So let's go back here. I assume that most of you have got it until here, right? And so let's look at these things over here. Remember in your input file, I told you to make a change, which is respect to the random filling, which is what you did, and you got a random distribution of precipitates, or well, grains. What you have given is a 45-degree rotation to your anisotropy, which is why all of your shapes are looking cubic. Okay, that is the reason they are looking cubic. Otherwise, if I had given isotropic, they would have remained circular. Isotropic means if the anisotropy is 0. Okay. In the other case, if I had rotated, as you have seen in the function f1, if you rotate by 0, it would be a diamond shape over here. All right. So this cubic shape is not because of any other aspect. It's just because your anisotropy, that rotation that you have given, is 45-degree rotated for the z-axis. Second is, let's go to composition, which is plotted like this. As we had done before, you can look at this. This is called plot over a line. All right. And you can apply. So it will give you something. But then you can choose what to plot. So you can scroll this bar down and choose to plot certain variables. So we'll choose the, we'll unselect this, can make mu al, which is the chemical potential, and plot only the composition, for example, because there's a lot of data. So we'll unselect alpha, liquid, and we'll plot this. Okay. Everybody able to do until here? Why is it not going? Okay, we will look at this. So now let's see what is happening. It's very quickly, whatever it's simulated. You are simulated, I mean, the growth velocity is so much that you started with something which is small, but immediately grew into something which beyond which it can't grow anymore. So can anybody tell me why do these guys stop here and not grow against each other? No, but why do they stop here? It's like they're hitting a wall, no? Why do they do that? So just look at this again. It appears that it is grown only that much and then stopped. Why? Huh? What? Well, it has something to do with the filling that there's so many of them inside. But why do they stop? Yeah, how? It's not hitting it, no? Yes. Well, that is filling, but during growth, that not is active, no? I'm not checking for shielding distance there. That does that give you a picture? Like, this you don't worry about. That's the starting. This should give you a picture. Let me go slowly. Previous frame. Let's go slowly. Okay. This is somewhere in between. Previously it was here. Then in one step ahead. Here. And as soon as the this became uniform, there is no more growth. You see, there's no more growth. Why is that? It's something to do with chemical potential. Huh? Huh? Who can tell me? Huh? Well, not heat. Temperature is uniform here, so there is no manifestation of heat. I'm plotting the chemical potential here. It's all uniform, no? I can't hear you. No more diffusion, and therefore no more growth. Yeah. So, because we are storing less files. We are storing only at time steps of 1,000. By 1,000, everything is complete. Okay. So the last evolution that you actually saw was somewhere here before impingement. So this is essentially referred to as soft impingement because you're not really impinging, but the composition fields are touching each other and essentially becoming uniform. And since the composition gradients and the chemical potential gradients are coming down, your supersaturation is lost and therefore growth stops. And you go to the stage of coarsening. Even after this, what you essentially will have only coarsening effects. That means the small ones will shrink, the large ones will grow. And that's a long time step process. If I leave this simulation now, for a long time, essentially what will happen is the small ones shrink, large ones grow, and eventually you will have fewer precipitates remaining with time. All right? That is, the coarsening is essentially interfacial phenomena because the composition at the interface is determined by the size of the precipitate and thereby also the diffusion. Okay, very good. Everybody understand what we have gone through here? What? Whatever, I didn't get you. Ah, yeah, something like this. You like this one? No, no. This is how you will see actually if you do a etching of your microstructure, you will see something like this. Because in principle, what you see here is precisely explained. Yeah. All right. Clear? Whatever we are seeing, any more doubts? All right. So let's do something interesting now. We have, let's do multi-phases. Multiple phases. Okay. Very good. So let's go back and import in file. Choose in file. So go to that same folder that Chinanthan has given you and go to aluminum zinc eutectic. Okay, and choose input alzn4.in. Okay, And it will tell, oops, we have noticed some missing parameters. Don't worry about it. Okay. Everybody able to find the infile? Okay. So you see the mesh is elongated in a certain direction. Okay. And that is because we want to grow in this direction. Okay. This is going to be directional growth. So I want to grow my eutectics in a given direction, and that's why it is elongated in a given direction. Okay. That's why that is going to be my growth direction. So let's have this. Dimension typically all stays the same. You notice here, number of phases is now 3. What are the 3 phases? You have alpha, beta, liquid. All right. And next. So same time steps, 20,000 and 1,000. And here again, I have chosen equilibrium values corresponding to what I want to have. So 0, 0, 0, 2, 1, 1. So these are the solid compositions. This is the liquid composition. Rather, sorry, 0, 2. The one. So all combinations with 2, which is the last phase, are the liquid compositions. Rest are the solid compositions. Don't worry about it right now. If you have a doubt, I'll come back to this. Okay, so let's go to boundary conditions. P mu. Notice what I have done here. These boundary conditions, this is X plus, I am putting PBC, which is periodic boundary condition. So this and this are periodic boundary conditions. Whereas I am having this and this as Neumann boundary conditions. Okay. Why is that? Because essentially I want to have in alpha beta, you want to have a situation that one lamellar unit of alpha beta growing means a repetition of alpha beta that can grow. So it's natural to have a periodic boundary condition in this direction and a growth in the y direction, which is Neumann, right? So this is what we will impose. And let's go ahead. So what do we fill here? We will import a filling. Okay, it's a slightly complicated filling. So we'll import shape so that we learn to import shapes as well. So you go here, go to sys array and go to aluminum zinc eutectic, and there's a filling file. Input the filling file. Okay, so it will fill the domain with something like this. Please come to this stage and tell me if you are able to do it. Done it? Able to do? Okay, everybody? All right. So then we go ahead. Next, these are all the same. And here I'm going to use the shift. Okay, shift is on, and I'm going to shift as soon as I reach 30 cells in the solid. That means the shift operation will start to happen as soon as I have grown about 30 units into the domain. All right. So let's go ahead. All of this noise is 0. This is 0. So let's get our new infile. And generate. So it will take you to the same place where you chose the infiles from. Just choose it. So it should tell you successfully created input files and then run. Okay, so you should come to this running stage. Tell me if you have come here. Okay, so you have alpha, beta, liquid now, 3 phases, because there are 2 solid phases and 1 liquid phase. There's a eutectic in this aluminum zinc system, which is what we are simulating. All right. So it simulated something and quickly gave us some output. We will follow the same thing that we have done until now. Okay, so are you all able to get to until this point? Ah, get to this point. Huh? Mine is a i7 3 something H processor. It's a high-end processor. Yes. I have some super power here, which I'm not using entirely. Are you all able to get it until here? Yeah, don't worry about the num workers in the int file. That is of no consequence. That's the obsolete key. So, I mean, that was a key when we used to reconstruct the. So when you reconstruct it from a file for restarting, you needed the number of workers because you need to locate the number of folders. But now you don't need it when you have an H5 file, so that's obsolete. That is where you need the create job script. So when you take that option, the job script creates the number of codes according to your wish. Everybody able to get it until here? Okay. So this is essentially a UTech tick. So one of the phases is alpha, one of this beta, and you see it is invading one phase. Okay. It is trying to get to the correct volume fraction, which it is not right now. All right. So you initialize the system at 50-50, but corresponding to the phase diagram, the volume fraction is not 50-50. Okay. So it will try to arrive there. But for that, we have to run a bit longer. So let's do that. Let's run it until 1,20,000. So go here and make it, I'm going to make it 2 lakh. All right. And I'm going to run, which would give me 200 files, which I don't like. So, okay, let there be 2. I mean, it's running pretty fast, so 2 lakh will be over in no time. So, no, I just increased the number of iterations to 2 lakh. Is running for them? Running? This is 100 cost 50. Okay, so for me it's done. Okay, so I will just check. Yeah. Okay. Okay. You see it starts to appear as though it has achieved steady state, right? With its right volume fraction. If you grow it a little bit longer, you would get the right volume fractions coming out. All right? And there are two phases growing, right? So it's a good idea to typically have it colored nicely. So let's do that. You can create in ParaView phases. So I can say that I'm going to color alpha with 0, beta with 2, plus liquid with 3. Okay, and apply. So then you can visualize the entire information in a colored format. Those three phases are going, right? And you see how this shifting is happening? You're moving in the moving frame such that you can do the large simulation. Right? So this phase diagram, it is essentially going to the right volume fraction given by the phase diagram, right? Because the connection with the thermodynamics tells it that given this liquid composition, this is the right volume fraction to come out with, right? So it automatically selects it, right? Well, it's going to end. So if you write a bit longer, it will be steady state. Okay, everybody able to get until here? Run for all of you? Still running? Okay. Let it finish. So let's do a ternary simulation after this. And how many of you are feeling sleepy? Right? Good, excellent, fantastic. We'll start in the morning 11. Yes. Yes. You're able to come until here? Still running, huh? How is it running? Just show me. No, no, I'm seeing the. It's stuck. Why is it not evolving? Oh, it's go here, go here. Where is the scroll bar? Where is the scroll bar? Bottom of the file. It's fine. Kiki. It's almost ending. So. Everybody comment here. So after this job ends and we are able to visualize, we'll break for the day. All right. And we'll continue tomorrow.
You can decide how much to shift.
I typically shift after I decide to check to shift every 1,000 time steps. And if you have gone beyond the threshold, then I shift and bring it back to the place where. No, I wanted to restart the simulation. So it checks the to restart. Done, huh? Everybody? Done, huh? Everybody? No? Still running. So since you are still running, I will restart.
So whenever you reset, it is adjusted.
Yes. Small it is.
You notice that aluminum is adjusting every now and then. It's shifting. That time it's adjusting. Now it has Nothing much.
Only to run 50,000. Oh, the two instances. Steady state.
No, just come.
So Rupesh, where were you? So your steady state has come. So that's because of the dynamics. It doesn't know now where it's, so dynamically it will approach it. By the way, there is a regime in which this will continue to happen. These also not die down. So beyond a particular spacing, there is a regime when this will be beautifully keeping on oscillating. Yeah.
Experimentally seen in video.
It can do that peacefully, dancing. They can also dance in different ways. They can dance like this, or only the big guy dances.
Small guy goes.
Small guy just maintains its shape.
All videos are available. Some of them favor. Taken videos.
You can simulate it. So eutectics a lot of fun. You can do. You want to create a pyrotechnic? Let's do a pyrotechnic tomorrow. Sure. Why not? Okay, so guys, we'll end it here today. All right, and call it quits for today and assemble tomorrow.
So if your computer has run some simulation, it has been useful. The real power of the computer.
You see, you can do very useful computations just on your laptop with the software, right? Okay, guys, online participants, we are ending for the day. Thanks for joining. Meet you again tomorrow at 11.